Functions. Today we're going to learn what a function is. Functions. What is a function? Does anybody know? Here's the easy of it. A function is a rule. Plain and simple. A function is a rule. Usually you guys see functions like this. Maybe y is equal to f of x. That's what you're familiar with. Well, what is that? It's a rule. It tells you that if I give you a number for x, here's what you should do with it. That's the rule. It's a set of instructions. Here's what you should do to the x, and then your output will be y. Okay? So in each function, there's two very important components. There's the x. The x is going to be the input, and it's also known as the independent variable. And then there's the rule f, which tells you what to do with that independent variable. And then what happens is it spits out some sort of output. That's the y, and we call y the dependent variable. The reason we call this one the independent variable is it's independent of anything else. There's nothing that tells you that x has to be one thing or another. That's where the choice is made in the input. And then after you apply the rule, then you get a fixed output which very much depends on what the rule is. That's why y is called the dependent variable, because it depends. It depends on the rule, it depends on the function. So try to remember it that way. X is the input, the independent variable. Y is the output, the dependent variable. Okay, you guys have probably seen functions before, but let's just check and make sure that you know how to evaluate a function. Okay, so let's practice a little bit with evaluating a function. Let's say that I give you f of x is equal to x squared plus 2, and I ask you what's f of 0, what's f of 1, what's f of minus 1. Why don't you go ahead and pause the video and try it out to make sure you know how to evaluate a function. Okay, so what you want to do is you take the value for the independent variable, the value for x here is 0, and then you plug it in right where you see the x, you square it, add 2, that's the rule, and you get 2. So here f of 0 is 2. What was f of 1? Same thing, you put the 1 in there, you square it, you add 2, 1 plus 2 is 3, you got 3. Last one I asked for was f of minus 1. What happens is you take the negative 1 and you square it, but here, make sure that you understand what it's saying. It's saying to square the entire quantity, square the 1 and square the negative sign. Okay, whatever you put in there, you have to square the whole thing. Add 2, and again you see minus 1 times minus 1 is positive 1. So again we get 1 plus 2, and we arrive at 3. Okay? Is this a function? Yes. What defines a function? A function is defined as anything where each unique input yields a unique output. Okay, so let me write that down. Each input yields one output. That's what makes a function a function. As long as you give me an input and I can apply a rule and get one unique output, I'm going to call that a function. Here, if you gave me 0, I got 2. You gave me 1, I got 3. You gave me minus 1, I got 3. Okay, this is the typical way that you're used to seeing a function, but there's actually other ways that you can see a function as well. Another common way that you might see a function is in a table setting. So let me show you that, and I'll ask you for some functional evaluations given a table-like setting. Now this is something that might actually happen to you in business because sometimes we define functions through observations. Let's say that we have some x and we have some y, and we observe that when x was 0, y was 14, when x was 1, y was 12, when x was 2, y was 11, when x was 3, y was 17. This is a table of values. Again, x is here is denoting the independent variable, y is denoting the dependent variable. And again, I could ask you for what's f of 0, what's f of 1, what's f of 2. And if you have it in a table like this, it's as simple as just reading it right off the table. So I'm not even going to ask you to pause for this one. You can probably see the answers right in front of you. F of 0 is 14. F of 1 is 12. F of 2 is 11. Okay? So that was a function, that was a function. I know that they're functions because for every value of the independent variable, I've been given a unique value of the dependent variable. Now let me show you some examples of something that's not a function. Might be easier for me to do this in the table setting here. It's not a function if you give it one input and then it comes out with more than one output. Okay, so here's an example of something that's not a function. And I'll give this to you as a table, and then once we introduce graphs, I'll give it to you as a graph too, examples of something that's not a function. Okay, so again, independent variable, dependent variable, 0, 1, 2, 3. Let's just put the 2 and the 3 there again. This is where we're going to start to run into trouble. 0 goes to 14, 1 goes to 12, 2 goes to 11, 3 goes to 17, 2 goes to minus 4, 3 goes to minus 6. What? What's the rule here? If you're going to be a function, for every value of x that you give, it has to be mapped. Sometimes the function is referred to as a map. It must be mapped to a unique value for the dependent variable. Here the 0 goes to 14, that's fine. The 1 goes to 12, that's fine. The 2 goes to 11, but down here, I also said that the 2 goes to minus 4. So which way is it? Does the 2 go to 11 or does the 2 go to minus 4? That can't be. That's why it's not a function. If one input yields more than one output, what you have there is not a function. Okay, so that's an example of something that's not a function. One way I really like to see functions is not so much as algebraic expressions or in the table format, but my favorite way to see a function is to graph a function. Okay, so let's go into graphs a little bit here. Now your typical graph is going to have two axes. We're going to have the x-axis here for the independent variable, the y-axis over here for the dependent variable, and all a graph really is it's a visual representation of the numbers that we were given. Okay, so for example, let's say f of x is equal to 3 times x. Okay, so that means if x is 0, 3 times 0 is 0, so y is 0. If x is 1, 3 times 1 is 3, so y is 3. If x is 2, y is 6. If x is 3, if x is 3, y is 9, etc. And what kind of function do I have right here? Try to make it a little nicer. That's a linear function because all these dots, if I really had drawn it properly to scale, would have lined up on the very same line right there. Okay? So that is a function. And now back to not a function as a graph, we have a special fun little test that you can perform on any graph that you see, and it will automatically tell you whether it's a function or whether it's not a function. Okay? That's called the vertical line test. So let's practice this vertical line test and see how it matches up with the definition that we've already talked about. Okay? Let's say that we have a graph of a function on the xy axis like this. What you want to envision is envision yourself drawing every possible vertical line that you could draw. So picture yourself drawing this line, that line, going through the entire x-axis, walking across the entire x-axis from left to right or vice versa, and drawing a vertical line everywhere. If that vertical line, the black line that I drew, intersects the graph of the function, which is the blue line here, exactly only one time, and no more than one time, then it is a function. Okay? That's because the graph here, remember, the independent variable is along the x-axis here, so this is like a value for the input, or this is a value for the input, etc. For each one of these values that I'm picking with my vertical line for the input, only one unique output is determined. That's what makes it a function. Now let's contrast that with another picture. And actually, I'll just draw the graph of f in a different color than I draw the axes, so you don't confuse it. So here's a graph in green of another picture, a graph of something anyway, of f of x. Question is it a function? It will only be a function if it passes this vertical line test. Okay, so that means that for every line that I draw here, well here the function doesn't exist, so you don't want to really consider it. Over here, how many times does my vertical line intersect the graph in question? Intersects it here and as well over here. That's a problem right there. That's not a good rule. That's not a valid rule for me. What are you trying to say here? If my input is the number 3, did you want me to be this value up here, or did you want me to be this value down here? Didn't make up its mind, and so it's not a function, because it's not a proper rule where I can say that for each unique input that I decide on, I'm going to get a unique output. It's just not happening here. This one fails the vertical line test. This one fails it. And this one passes it. And keep in mind that if you're going to use the vertical line test to determine whether or not something is a function, it has to pass the test everywhere, for every value of x possible. So let me give you another one, maybe a couple more, and you guys can determine for me, are these functions yes or no? Okay, I'll draw the function in green. And now you visualize yourself doing the vertical line test on each one of these functions. Is it a function? That's my question to you. If it's not a function, well, what's the problem with it? Why not? Is it a function? Okay, so let's check it out. I use black for the axes, so maybe I'll do my vertical line test this time in red. And remember what I was saying, you have to do it for every single value, here, 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 here. This looks like it checks out okay. Every time I do it, it's just intersecting the graph one time, which means that for every unique input that I give it, I yield a unique output. Over here, what do you guys think about this one? Can you see it? Can you see the problem? It's fine, it's fine, it's fine. Everything's going fine until I hit that little curve in the road. And if there's any problem at all, then the answer is no, not a function. Not a function. It's not a function in general because of this problematic spot here where the curve doubles back upon itself, so that for this value of the independent variable here, I have 1, 2, 3 given outputs. That's very confusing. Don't do that in math. You can't give me one thing and then expect to get 3 things out. Okay? So those things are not functions. Alright, now let's go on to the concepts of domain and range of a function. Okay? Maybe you guys have heard of this before, maybe you haven't, but domain and range are very important to consider when you're doing any type of problem, because especially for the domain, you must always work inside the domain of a problem. Okay? So I'll give you some definitions. The domain is all the values of x that can be used as input. Remember x, the independent variable, that's what we're putting into the function. And the collection of every single value of x that's okay to throw into that function is known as the domain. Okay? And then we have another concept for the range, and that has to do with the y, and that's all the values the function can give as output. One of these has to do with the input. The domain has to do with what's okay for the input. The range has to do with what kind of values can we reach with that function. What kind of values can we obtain as the output? Now I'm going to draw a picture of a function, a graph of a function, and then we'll talk about visually where to find the domain and the range. Okay, I'll give us two examples. Alright, so these are two separate functions, and the first thing that I would want you to do is visually confirm for me that these are indeed functions using the vertical line test. And if you do that, you should come to the conclusion that yes, they are. They're both functions. And now, on to the question of what is the domain of each of these functions, and what is the range of each of these functions, and these things have to do with the x and the y respectively. The domain, all the values of x that I can put into the function. Looks like all these values over here are just fine. -8, -6, -4, 0, that's fine. 1, 2, 3, they're all fine. Looks like every single value of x that I can think of is okay to put into this function. Therefore, I'm going to state that the domain is that x can be inside -infinity to infinity. Okay, so this is basically all real numbers, and another shorthand notation that you might see to show that this is all real numbers is that x is in what we call the Blackboard Math bold R. This R right here stands for the real numbers, all of them. All the numbers from -infinity to infinity. And if you're wondering what this little symbol is, this symbol means in. Okay, so this statement right here is read as the domain of this function is x is in the real numbers. It can be any real number from -infinity to infinity. Okay? Now let's contrast that with what we see over here in this function here. It looks like if I give you this x, I'll get that for y. This x, got that for y. What about over here? If I give you this x, what am I going to get? I don't know. There's no picture there, actually. So these numbers over here, where there's no picture line for the graph, these are not in the domain. Domain is all the values that can be used as input. Well, I don't see any statement of what the output would be if I put this for the input. So they're not in the domain. So the domain for this function is that x is in the interval from 0 to infinity. Because you can see positive infinity, from 0 to positive infinity here, that's all just fine. The negative numbers are not fine. Alright, so one thing that I want to be a little bit specific on, the nitty-gritty here, is that I use a square bracket here next to the 0, and that's because when I look at this graph, the value at x equals 0 is included in the graph. Okay, square bracket means to include that specific value of 0, and it is included. Alright, so let me just contrast that with what you would see if I had drawn a picture like this with an open circle. If I drew an open circle there instead of a filled-in circle, that would mean that you cannot include the 0 in the domain. And that would change my answer for domain from this statement here. I'd have to erase the square bracket and put an open parenthesis like that, which says I am excluding that point. You can't put in 0, and I was reading that off the graph because it's an open circle right there. Okay, so we'll continue this example with the open circle in place, and just keep in mind that that's what that means. Alright, so that's the domain. It has to do with the x. Now we're going to move on to the range, which speaks about the y. It tells us what are the values that can be reached. Okay? When you're looking at this picture, you can see that if I want to be up here at the number positive 10, I could use that value for x to get there, or I could use that value for x to get there. I can get to this height. How many different heights can be reached? These y values here, these heights, are the range. Any of these seem fine. What about this height down here? What if I wanted a height of -3? What x value would give me that? I can't get it. I just can't get it out of that. So that's not in the range. The range is going to describe all the y values that you can reach. So here you can see that it seems like from 0 all the way up to positive infinity, those are the y values that I can reach. So my range is going to be that y is in the interval, including the number 0, 0 to infinity. And again, how did I know that it included 0? That's the nitty-gritty of it, because I can see it touching the x-axis right there. I see it touching. Okay? And maybe you can contrast that to the other function here. If I had an open circle there, the open circle means I couldn't put x equals 0 in there. And can you actually get y equals 0 out of it? You can't, because it was intending to go through the point 0, 0, and if you can't get the x0 in there, then you're not going to get the y0 out of there either. So for this one, the range is that y is going to be in 0 to infinity, and it excludes the 0 point, where here, this one, it touches it, and it includes the 0 point. Okay, so that's how to graphically determine the domain and range. And I'll throw a couple more examples up here for you to graphically determine the domain and range before we move on to an analytical determination of the domain. Okay. Oh, that one's a little crooked. For each one of these, I'd like you to state for me what is the domain and what is the range. And here I'll draw the graph in blue. Okay, domain, range. I'd like you to write these in the interval notation that I was using over here. Pause the video if you like and write down your answers for domain and range. Okay, remember, domain refers to the x, range refers to the y. So here in the domain for this function here, do you know what type of function that is? That's right, it's a linear function. I meant to draw it perfectly straight. It's just a straight line that is going down. What types of x's are okay? Well, I could use any of these values of x, so that means that x can be in the interval from -infinity to infinity. Some people have asked me before, why do you have an open bracket here at -infinity, an open bracket here at infinity? Why don't you use a square bracket to include them as you did for the number 0 here? The answer is because infinity is actually not a real number. Infinity is not part of this set called the reals. It's an abstract concept, which is that this is a value that's greater than any finite real value that you can state. Okay, so this is purposefully written as an exclusive, not an inclusive, because infinity is not a real number. And I'll have to tell you, if I see this on papers, this is incorrect. This actually gets taken off a little bit of points because infinity is not a real number, so you can never include it in an interval notation set. Okay, so please make sure that you don't do that, and whenever you have an infinity, you use a parenthesis. Okay? Alright, the domain is, I can put in anything to this one, and then the range asks the question, what can I get out of this function? Can I get a positive number? Looks alright. Can I get a negative number? Sure, if I go over here I can get some negatives. Turns out the range is everything. I could get everything out of this, and so just like the domain, the range is the interval from -infinity to infinity. Okay, so let's try this example over here. What kind of inputs are okay for this function? All of them. It's totally fine. Remember, when you're thinking about the domain, you want to look at the x-axis here and see which one of the values along the horizontal axis has a corresponding point on the y. They all do. However, all the corresponding y values are negative. and that speaks to the range. So when I ask you what the range is, you can't get a positive value out of this function. You just can't. No matter what x you put in, you just keep getting negative values. And so that means that the range for this y is negative infinity to 0. And it does include the 0 point because it touches what we call the origin. Right here where those crosshairs cross and x and y are both 0, we refer to that as the origin. So because that point is being reached, we include 0. Because infinity or negative infinity is not a real number, we can never use the square bracket on those. Okay, so hopefully you feel alright with this graphical depiction of functions. Now I'll discuss a little bit about how to determine the domain analytically. And by analytically, I mean by just using the equation and not looking at the graph. Keep in mind that if you do have all your resources about you, if you have your graphing calculator with you, it's always great to have more than one thing at your disposal. So if you can have a graph, you should get the graph as well. But now we'll go into determining domain analytically. All right. Now, there's two things you have to consider. You have to consider in just the mathematical setting, mathematically, or you have to consider that in the context of an application. Okay? Mathematically speaking, when you put something into a function, it's okay to do that as long as you don't disobey two critical rules. The first rule is, number 1, don't divide by 0. You just can't. What's 3 over 0? You can't. You can't divide by 0, so don't do it. And if there's a value of x that's causing you to divide by 0, it is not in the domain. The other thing that you can't do over the real numbers is you can't square root a negative number. What's the square root of negative 1? Actually, mathematically, it has a value. It's called I, the imaginary number. But I is not a real number. Over the set of the real numbers that we're talking about, you cannot take the square root of negative 1, and you cannot take the square root of any other negative numbers. So if your equation is telling you that for the number that you put in, you're going to have to square root a negative, you can't do it. So that input is not in the domain under that case. These are the only things that can go wrong mathematically. So let me show you some examples of that, and then we'll discuss further things that can go wrong when you're actually using a function in the context of an application. Then you have to consider the things that make sense for your chosen application. Okay, so here we'll go into the mathematical examples. Mathematically speaking, let's say that f of x is equal to the square root of x. Okay, so where do you think I'm going with this one? You can't square root a negative number. I can square root a 4, I can square root a 6, but I can't square root a negative 3. And so the domain for this function is x must be greater or equal to 0. Or, if you like to write it this way, x is in the interval including 0 all the way to infinity, but you cannot include the negative numbers. Okay? So either one of these is acceptable answers for what is the domain of the square root of x, as long as you're not square rooting a negative number. Let's do that one again, except let's make it a little more complicated. What if it was this, 2x plus 4? The square root of 2x plus 4. What's the domain of that function? Pause the video and see if you can figure it out. I haven't shown you one like this before, so it's kind of a puzzle. Okay, so how I wanted you to figure this out is that the thing that's getting square rooted cannot be negative. So what we need to solve out for is where are the places where 2x plus 4 is greater or equal to 0. This is what's inside the square root. What's inside the square root must be greater or equal to 0. 0 is included. What's the square root of 0? 0. So that's okay. All right? So now you see that this problem, searching for the domain of this function, has led me toward an inequality, which I must find out, solve out for x, and see what are the values of x such that the thing that's underneath the square root will always obey that property. Okay, so then I'm going to have to solve that out. 2x is greater or equal to -4. I get that by subtracting 4 from both sides. Next, I'm going to divide both sides by 2 and get the statement that x must be greater or equal to -2. So that means the domain for this function right here is that x is greater or equal to -2. Or if you like, you could write it this way. -2 is included, and you can go all the way up to infinity. Can you put in -3? 2 times -3 is -6, plus 4 is -2. That would be the square root of -2, and I can't. So you see, that's how that works out. If you ever see a square root, make sure what's inside the square root as a whole obeys the fact that it's got to be greater or equal to 0. Okay? So now we're going to move on to the other mathematical no-no, which is don't divide by 0. I'll show you a couple examples of that. All right? So for example, what if we have f of x is equal to 1 over x? Start simply there. You can see that just including a fraction that includes division is already enough for me to say, hey, wait a minute, I have division here. Am I going to divide by 0? For what values of x would I divide by 0? 0. So that can't be in the domain. So when I ask you what the domain of that is mathematically, you have to say all the x except this one. X can't be 0. So you can write it like this, or you can say, well, what are all the numbers besides 0? What numbers are okay? Minus infinity to 0 is okay. But you see, I got the open parenthesis because 0 is not okay. And then also, and 0 to infinity, those are fine too. Okay, so this statement says everything but 0, and this statement also implies everything but 0. Either one of these are a fine answer. All right, now I'd like you to try it again, something a little more challenging. Go ahead and pause the video and write down the statement for the domain of that function. Okay? So if you said that the domain here was that x cannot be 7, that's exactly what I was looking for, because 7 is the exact number such that I would divide by 0. Don't divide by 0, okay? So you can write it this way, or if you like, you could say, well, I can go all the way from minus infinity all the way up to the number 7, but I can't include it. And then after I've excluded that, I can go on to positive infinity. All those are just fine. Everything but the 7. Okay? Now, that's just the world of mathematics where these expressions, these functional expressions, haven't been given a context. But really, honestly, why are most people doing mathematics? Not just for the joy of it, but because they want to apply it to something. So in the context of an application, you have to actually look out for other things that are going to exclude values from your domain. Here's a great example from business. So business application, how about cost or revenue or profit? So here I've got C of x, R of x, and P of x for cost, revenue, and profit respectively. And in all of these cases, x, let's say, is the quantity or the number of items. Okay? So that would be my cost at a certain number of items, my profit at a certain number of items. What is the inherent domain, without even writing down the mathematical expression for these? What do you think the inherent domain is going to be for these types of functions? The number of items produced, the number of items sold. Can I make negative 20 items? No, not in my real world shop. I cannot. So x inherently for this domain has to be greater or equal to 0. You can't sell a negative number of items. You could make 0 items. That's why I included 0. So the domain here the domain has to be greater than 0, or if you like, including 0 and going all the way up to infinity, either way. Okay? So that's what I mean by something like in the context of an application, because for example, if my revenue, if I'm selling lollipops for 25 cents each, my revenue is 25 cents times how many pops, what's the domain? A lot of people say, well, mathematically you could put any real number in here. You're not square rooting a negative, you're not dividing by 0, but what are you doing? You're mathematically modeling. And if your x is a number of items, your domain has to match that concept. Okay? I've got one more example for you from a business application. Let's say that we have percentages. In business a lot, you have to deal with percentages. Well, let's say that we have P, which is the percent of a job that's completed. Okay, so maybe I've got some team working on a job, and when they start, they're 0% complete. When they're done, it's going to be 100% complete. Without even writing anything down, anything more down, where do you think I'm going with this? What do you think the domain for P is? Yeah, P is going to have to be between 0 and 100%. You can't be more complete than 100% done with the job because it's over. There's nothing left to do. You can't be negative 20%, let's hope, done with a job unless you made more of a job when you showed up. So what I'm saying is I want that domain to be between 0 and 100%. Okay? All right, so that's domain and range. And now let's go into a little bit about how to perform operations with functions. Sometimes you'll have more than one function and you'll have to combine them together. Just like I had the cost and revenue and profit, do you guys remember what profit was? Profit, in terms of revenue and cost, you remember? It's the revenue, it's the amount of money you make, and then you subtract away the cost. Okay, so this is a lead into my next topic, which is how to combine functions, adding them, subtracting them, multiplying, dividing them. Those are all what we refer to as operations on functions. Okay, so most of these operations are going to be very familiar to you. The main 4 operations we're talking about are adding, subtracting, multiplying, and dividing. Okay? So I don't think I have to write out the words for that. Adding, subtracting, multiplying, and dividing. And if you have 2 functions, let's say you have 2 functions f of x and g of x, then if you want to add them together, you're more than welcome to do so. You can just say, what's f of x, and then just add g of x. If you want to subtract them, go for it. What's f of x minus g of x? And you can see an application of that right here. Sometimes you're going to have to multiply 2 functions together, and how it's done is just in a very normal fashion, f of x times g of x. And then dividing, same thing, you just define it as f of x divided by g of x. Okay, so there's one for profit right there. Let me give you another business application of that real quick. And that would be, let's do multiplication. Let's say that we have x, which is the number of items that I'm selling, and we also have p, which is the price of one item, okay? How am I going to form my revenue equation? Remember, the total revenue is the amount of money that you're going to make all together when you've sold all X of those items at a price of P per item. You got to just multiply them together, just like I did with the lollipops, 25 cents a pop, 25 times X, or 0.25 times X. So your revenue function here would be the price per item, and then multiplied by the number of items. Okay? So you can see you just multiply them together. Inherently, these are very simple functions here. X is just the identity function. X is equal to X. And P is the price. I won't go into it too much right now, but later I'll show you how to mathematically model your price. because you know that the price demand is a thing like, if the price is higher, people will want less of it. If the price is lower, people will want more of it. That's the law of demand. So later I'll show you how to turn this into something that depends functionally on the number of items demanded, and then you'll see that in more detail, the operations on functions. We just have one more operation on function. I think that's a little bit different from the 4 familiar ones here. And that's an operation called composition. This is something that you may not have seen before. Composition of functions, but will be useful to us. This is when you put one function inside the other function. It's called composing two functions. So again, let's assume that we have f of x, and then separately we have a function g of x. We can compose them and form a composition. We'll call it f of g of x. Or some people like to write it like this, f composed with g. This is the more common way to write it. I would prefer to write it this way because it's more clear what you're doing. What you're doing inside a composition is you're taking one function, the output from the g function, and you're throwing it inside the f function. So you're doing f of g of x, okay? Computing g of x and then using that as the input for the function f of x. Please note, this is not multiplication. This is not multiplying f times g. It's evaluating g and then putting that inside the f and then evaluating f from there. Sometimes it's written as f and then a little circle and then g. Okay, I'll stick to this one. You can do this you can do f of g of x, you can do g of f of x. You can compose a function with itself. Let me show you an example of composition so you can get more comfortable with it. Let's put some actual algebra to these functions. Maybe f of x is equal to negative x squared plus 4. Maybe g of x is 2x. Okay? So now we have a concrete example to work with. What I want to see is, what is the composition? What is f of g of x? What happens when I compose these two functions by using g as the inner function and f as the outer function? Okay, so keep in mind that the one that goes inside is denoted as the inner function. Okay? And the one that appears on the outside right here, the f is on the outside, that's called the outer function. And now let me show you what the composition is by example. What you're doing is, eventually what you want to do is evaluate f of x, but instead of using x, where you see the x here, you're going to use g of x. Let me do this using the colors that I defined these two functions with. Okay? The answer to this problem will be yielded by copying down f of x. I'll do it in black because it's the outer function. Copying down the f of x. Okay? But here's the kicker. Wherever you see the x, erase it. You have to replace the letter x in the outer function with the entire expression. So I'll use parentheses because you have to replace it with an entire function. You have to replace that with what g of x is. And what's g of x? That's 2x. So I have to put the entire 2x inside of there. Okay, and then I'm going to simplify that out to whatever expression that it comes out to. And you can see that here, the negative sign, 2x quantity squared is equal to 4 times x squared. Don't forget to square the constant. That's why I was very careful to use parentheses. Square the 2 as well, and then you're adding the 4. Okay, so f of g of x is minus 4x squared plus 4. Now I want you to try it. I'm going to erase this, but I'm not going to erase the functions. I want you to use the same two functions, but give it to me this way. Find what is g of f of x. Okay, go ahead and pause your video and find out for me, simplified, what is g of f of x. Okay, so this time the outer function is going to be the g. Alright, so I'll mark it with the colors again. This one's going to be outer. And then the inner function I'll mark in orange is the f. And this is the inner function. And what we do is we start to copy down the outer function, which is 2x. 2. But wherever we see the x in the outer function, we want to replace it first of all with a big parentheses, and then secondly with whatever was inside the parentheses. Here it's f of x, so now on the inside I'm going to have to put this whole thing. Okay? And then simplifying that out would just be by factoring the 2 through, so you would get negative 2x squared plus 8. So you can see that g of f of x, if you're taking notes and you still have the f of g of x on your page, you can see this is not the same thing as f of g of x. The two compositions are not necessarily the same thing. And let's just practice a little bit more to really hammer it home here. Why don't you guys practice these two for me? Why don't you find f of x, that's right, you can do that, and g of x. Not only can you compose a function with another function, you could also compose it with itself, and you could do that multiple times. You could do f of x. I won't do that one right now. But you could. So pause the video and go ahead and give me simplified expressions for both of these. Okay, so let's see how you did here. F of x is a little bit harder here because watch what happens. The outer function is minus something squared plus 4. And the inner function is actually the same thing as the outer function was, so inside here I have to write minus x squared plus 4. Okay, so that's the unsimplified answer here. You see I've got the f of x on the inside and on the outside. The hard part would be if they asked you to FOIL this out. Do you guys remember how to FOIL, factor out? Let me erase this one for now. If I actually wanted to simplify this out, I would have to say, well, that's equal to negative the quantity negative x squared plus 4 times negative x squared plus 4 plus 4. You see how I wrote out that squared as what it actually is as the product, and then for those of you who are diligent enough to actually FOIL that out and simplify that down, let's see what we get out of that. Okay, now don't forget about the outer negative. That one has to stay right there. And then we're going to do first negative x squared times negative x squared. The two negatives cancel, and the exponents add together to get x to the 4th. Outer, negative x squared times 4. That's negative 4x squared. Inner, 4 times negative x squared. That's another negative 4x squared. Last, 4 times 4, that's 16. Okay, and then we still have to add 4 at the end. So combining like terms, I've got x4 minus 8x squared plus 16 plus 4. Now factoring through this negative sign, which was present on the outside, I have negative x4 plus 8x squared minus 16 plus 4. And the reason I do that is because I'd also like to combine these two like terms, these two just number terms. And all in all, f of x is equal to this expression right here. And if you got that, great job. Okay, g of x is going to be a little bit easier than this. So let me just show you what g of x is. G of x. Well, outside is 2x, so there's 2, and then there's a big parentheses. Inside is 2x, so you just put the 2x right in there. So g of x is just 4x. That one was a little bit easier, huh? So you could probably do g of x pretty quickly. Hopefully you understand how to compose functions because we're definitely going to need that material. Let me show you one quick business application of the composition of functions here. Okay, so sometimes we have two different mathematical models, two equations that are describing two different things, and we will need to compose them. For example, let's say I just opened a brand new website. I'm trying to sell stuff on my Etsy.com website, and I have an expression Q of T, which is the quantity of items sold T days after the store opens. Okay? So 1 day after it opened would be Q of 1. 2 days after it opened, how many did I sell? Q of 2. That's the quantity that I sold on the Tth day, T days after the store opens. And then also, let's say that I have P of X, where if I did have my number of items X, this would be the profit in dollars for X items sold. Okay? Now you can see there's a little bit of overlap here. The input for the profit is number of items sold. The output for this function is number of items sold, the quantity sold. The output here is the same thing as the input there, and what I'm hinting at here is I want to form an equation for a composition of functions. What I want is an expression, P of T, which is the profit T days after opening. Okay? Now, P as input is supposed to take a number of items, and that's the output from Q. So I'm going to rephrase the output from Q as just X, and then I'm going to go ahead and put it right inside the P. Okay? So really, the expression which yields me the profit in dollars, T days after opening, is going to be equal to P of Q of T. P of Q of T. Okay? And so that would be a composition of functions right there. So let's just do that out with maybe a little bit of an expression to make sure that you would be able to do the algebra behind there. Let's say my profit P of X is like 20x minus 400, and then let's say X of T is 7 times T. Okay, so on the first day I sold 7, second day I sold 14, third day 21. Meanwhile, my profit in dollars is given by this function. So what's my profit as a function of T? Pause the video and try to work this out, seeing as I want this answer. What is P of T? Okay, so the question was, what is the function P of T? And P of T we can see as the composition, because P is taking X as input and X is taking T as input. So this is really P of X of T. That's going to be 20. This is me working on the outer function right now, copying down the outer function. And everywhere I see an X, I'm going to stop. And I'm going to put a big parentheses. And that's because usually where I would put an X, I'm actually going to throw a whole entire function right into the X. And so I'm going to put a 7t there, and so that's 140t minus 400. So there you go. That would be the expression of what is my profit in dollars on a given day, T days after opening. Okay.